Hello, my name is Mr. Auger. I am Highland Middle School's 8th grade math teacher, one out of three of them. And I just wanted to make this video to give a sample of how I do lessons. Now, it won't be the full range of the lesson because it really requires more than one student, but I want to be able to show you exactly how I unfold the lesson in some way or another. So today we are going to talk about something that a lot of people are like struggling with. In fact, about 50% of the adults around the world actually forget how to do these fractions. The thing about fractions is what most of us have missed in school because in our day they just said, here's a bunch of numbers, do something with it for a long time. And if you don't know what you're doing, then you should have known already. That's not very fair to the students, and I would never do that to the students as well. That doesn't do anything for them. It doesn't even create responsibility. It just creates a bunch of shame, and that's not cool. What really we should be doing is we should be understanding, and we should start from the beginning of what fractions really are. Let's take a step back and understand that math symbols are just representations of ideas. That's all it is. We use English, it represents a meaning, and that's kind of how we show our thinking. In math, we kind of only like one symbol to represent something if possible. Sometimes we have to use, more than one symbol, right? In this case, with fractions, let's identify the top number and let's identify the top number of a fraction. I'll draw a bar, which means division. We're going to separate, and then we are going to write something on the top. Let's choose red. What I'm going to write on the top is just a general representation. Piece. Pieces. Pieces. The top part of the fraction just represents pieces. The bottom part represents, and we must have heard this a lot, the pieces that make a whole. It's just I don't really get much success from that phrase, the amount of pieces to make a whole. That instead I've gotten more success by saying all the pieces, all pieces, all the pieces. It's kind of silly. I'm trying to use a mouse instead of my pen. So pieces, all pieces. Now we've learned that this could be represented as a word, and let's see if you can guess it, or see if you can remember it. It starts with an N, and it almost looks like number, but numerator. Numerator. What's interesting about this is look at that word numer in the word numerator. That kind of looks like a lot of like number, right? I would imagine it's kind of like that word number, like as in the number of pieces you would need, or not need, but rather have. And then what about the bottom number? What is that called? Do you remember? It starts with a D. De na min ater. Denominator. That's supposed to be an N. There we go. Denominator. All pieces, denominator. It, this word deno kind of reminds me of the word all. I know they don't really connect very well. My background is in kind of like another kind of language, like Greek, And Deno has some level of all to it. Not exactly, it doesn't represent it very closely. It just, to me, it does. So Deno, all the pieces. The top number, just the pieces. So if I were to visualize, let's say, I'll go here. Let's say this is just 1. And we could represent this as 1 over 1 because it's one piece out of the whole, right? But what if we were to cut it in half, right? What if I cut it in half and I do it twice, right? Or not twice, but I just make 2 of these little pieces. If I connect them together, you'll notice that instead of being 1 out of 1, now it's 1 out of 2 for both of these pieces. Now, the bottom number is a 2. The top number is a 1. The bottom number, it was a 2. It turned into 1/2, right? The top number, just a 1. This unit fraction here. That means there's only one piece. There's only one piece here. If I were to go ahead and delete it and just replace this here, look how it's just one piece. And it's 1 out of 2. 1 out of the 2 pieces it would take to make a whole unit. What if we kind of cut it in half again? Then what? My question to you is, how many of these yellow tiles do you think it would take? Whoops. How many numbers of yellow tiles would it take to complete an entire tile, one unit completely? If you guessed 4, you would be correct. And how exactly did you know that? What information gave that away? Right, it was the bottom number, which of course, again, is the denominator. The denominator represents all of the pieces it would take to make a whole. So you'll notice some difference though. Observe the difference between 1/2 and 1/4. What is the difference? I can't get this thing to work. Hold on. I think it's what makes teaching so interesting is sometimes we can't get technology to work the way we want to. Here we go. So look at this. I have 1/2 here. I have 1/4 up here. If I were to create another 1/2, look, we've created another whole piece by merging them together. Well, there's 4 pieces here, but there's only 2 pieces here. So one thing that we can observe between this bottom number of the 1/4 and the 1/2 is that there's more pieces. And look at the size difference. One of the most common misconceptions is when we think of fractions, we kind of look at the bottom number. Let's say I'm going to do this all in black to save us some time. Say we look at the bottom number and it's like, I don't know, let's go with like 5. And the top number is like 3, right? Oh, what if we had something like 6, 10? Well, they're not the same, right? Actually, they are. But the numbers are different. And you would be correct. These numbers are totally different. But why are they equal to each other? It has a lot to do with this information down here and this information down here. They are the same amount of well, they're not the same amount of pieces right now. And yes, the size, it's different. But notice that there are 4 pieces here making up an entire unit, and then there's 2 pieces here making up an entire unit. Notice that it's kind of the same thing. This would be 4 out of 4. This would be 2 out of 2, and both of those make a whole unit. Um, well, why do I claim that this would be the same size overall? It's because this 5 represents how many of the pieces needed to make a whole, and this 3 represents how many pieces I currently have. It could also mean how many are missing. This 10 over here means that it would take 10 pieces to make an entire whole, and I only have 6 of them. What that means is, as these numbers increase, what happens to the size of the piece? Yeah, it gets smaller. And that's where the confusion comes in. A lot of people get confused because they think as this number grows that this fraction should be big. And that's not entirely true. What we should think about is this bottom number not only represents all of the pieces, but like Dino might suggest, it represents all the pieces and a certain size as well. It represents pieces in size. So what does that mean? And how can we apply this concept to help us solve fractions? Let me see if I can get this a little bit bigger. How can we use this to help us solve fractions? Well, notice the bottom number. That's what we should look at first. So let's examine the size of these pieces first. And let's kind of take a look at a visual of it so we have a good idea of what it's representing. Now, from what I could tell, there is a 1/5 piece, 1/5 piece, right? And then in this, oh, excuse me, my headset turned off in the middle of this. Huh. Anyways, in this positive 2/5 term, we have 2 pieces. 1, 2. Notice that they're the same size. And notice that the bottom is a 5, which means it'll take 5 of these to make an entire whole. And the top number represents how many pieces. So let's count it. 1, 2, 3, right? So what if I was just looking at fractions and I was not looking at these tiles? What would I visualize in my head? I would visualize something that looks really close to this here. I know it's smaller than a whole unit. I know that it's smaller than a half of a unit. So I'm going to visualize something that would take 5 units to make a whole. Now, because these are the same size and the same amount of pieces to make a whole, I could simply just add the pieces at the top and say this would be 3/5. Why don't you give this one a try here? Notice that the bottom number is 11, both of them. So they must be the same size. And they must be the same amount to make a whole. So because they match, I can go ahead and remove, because that's what this term means. I started with 5 pieces. This minus sign means I will remove 4 pieces. That's what this information means. This is actually a math sentence. So if I were to visualize it, if I were to have, I don't think I have 11ths on here. I do not. Well, I wonder if I can apply the same exact idea, the concept, as this one I did, like they were the same size, so I know I could just add the top because the pieces were the same size and the same amount to make a whole. So do I even need to worry about this right now? Probably not. Let's go to this right here in our imagination and understand that the denominator is all the pieces that are the same size. The top number represents the amount of pieces present, could represent the pieces absent, but mostly present. And I have 5 of those tiles. Well, if I remove 4 of those tiles, how many would be remaining? And you probably guessed it, 1. What do you think about this one? I'll give you a couple of seconds. Right, the bottom numbers are the same. We could just go ahead and add the top. And without looking, at our fraction help over here, we could say that this must be 4 out of 7 units. Great. And it seems to be getting easy, right? The bottoms are the same. The top, 6 minus 4, 2 out of 8. Uh-oh. So we've run into a problem. Look at this. Now, normally in math, things seem easy at first, and then you're hit with something that looks different. Well, what are you going to do when the items are different? When the denominators are different, the 8 and the 4, what are we going to do about that? We gotta we kind of got to cut things into equal pieces, right? And look at this. This model here kind of helps us. We visualize what 1/8 would look like, right? And then we're going to subtract 1/4. What do you notice about the size of these pieces and the size of this piece? Okay, we got green. This one says 1/8. It'll take 8 units to make a whole piece. This one's blue. It's much bigger than the green piece, and it looks like it would take 4 of these to make one big piece. I also noticed that from this position to the left and this position on the left, if I were to kind of make them match, you'll notice that it takes 2/8 of a piece to make a quarter. What does that tell us? Well, that tells us we need to cut this in half. When we cut it in half, what do you expect will happen to this 4? Shall it become 2? Not exactly 2. If remember, when we have bigger numbers on the bottom, it means we have more pieces and that they're smaller. So cutting this bottom in half doesn't mean we'll divide 4 by 2, but rather the opposite. We're going to multiply it by 2. I have 2 extra groups here, right? So now I'm going to consider this 4, this 1/4, and my goal is to try to cut it so that 8 pieces will make a whole. Well, what would I have to multiply the bottom to get to 8? 4 times something will get me to 8. And if you guessed it, wonderful, 2. The thing is, I can't just cut the bottom without cutting the top, because then I just have different sized pieces still, right? Like I got to do something to the top of the fraction, because if not, if I leave it as a 1, this wouldn't make any sense, because I clearly see 2 pieces here. So I need for the top to change as well, and I need it also multiplied by 2. We're going to cut this one piece into 2. And also, take a look, 2 over 2. What is 2 divided by 2? If it takes 2 pieces to make a whole and you have those 2 pieces present, how many pieces do you have in all? I have 2 pieces. 1, 2. I have 2 pieces to make a whole. 1, 2. It makes 1. 1 whole unit. 2, 1/2. 1/2. 2 pieces. 2 over 2 makes 1. And 1 times any number is still the same exact number. Are you starting to see the reason why I might say that these are actually equal to each other, even though the digits are different? How would I get from a 3 to a 6? I multiplied by 2. How would I get to 5 to 10? I multiplied by 2 to the top and bottom of 3/5, and I got 6/10. That's why they're equal to each other. Now, yes, I agree the sizes are different. That is understandable. And yes, the different amount of pieces, but in all reality, once we put them together, it's actually the same size piece. It's the same amount of length. So what happens here? Well, the coolest part about fractions is you could just multiply straight across. So 1 times 2 is 2. 2 times 4, or 4 times 2 is 8. So really, what I have is I have 4/8, and I'm going to subtract 2/8. 4 minus 2, 2 over 8. Now, it's probably going to have me reduce this. I'm not sure because I haven't tested this one out yet. It should be 1/4, this right here. We're going to find out though. That maybe 2/8 would work. And then we learn how to reduce later. Aha! Okay, so we learn how to reduce later. So let's take a look at this model. We have 8 pieces of 9, and we're going to add 2/3 to it. So we need to make sure that we're developing a strategy, and this is something that you as a student are expected to accomplish. You actually have to create your own procedure by using just the concept, being there's a numerator, there's a denominator. The denominator means same size pieces. So you should be asking yourself immediately, how can I make these two bottom numbers the same pieces? Now I've seen students in the past just do something like this. I've seen a lot of cool stuff. I've seen 8/9 plus 2/3. And then what I saw the students do is they would write a little x up here and then times 2, and then an x down here and say times 2. But if I times 2, I get 6, so that's not going to work. What number can be multiplied by 3 and get me 9? If you guessed it, 3 times 3 is equal to 9. And then what they do is they rewrite it. 8/9. Uh-huh. 8/9. I drew a better 9 that time. Go me. Let's see. That's not a plus sign. That's a group sign. So 2 groups of 3 would make 6 in all. And then 3 groups of 3 would make 9. And now all I have to do is, now that the bottom number represents the same size and the same amount of pieces to make a whole unit, I can now add the top. So 8 plus 6. Let's see, I know 8 plus 8 is 16, and I know the difference is 2, so this must be 14 on the top. It's a mental math strategy that I used. Everyone has their own, and I encourage everyone to use it and share your own strategy. So it must be 14/9. So with that being said, we got to 49. I would like to see students get to around 80, as that represents mastery. And if you really want to push yourself, because remember, being good, or having good stuff on here is not exactly um, a, the best goal to have. It's a decent goal. The best goal to have is, how are you going to get to great? Just remember, one person has stated this. He's a very popular business author. He said, "Good is the enemy of great." So if you ask, is 70 good? I'm gonna say, I don't know. Define good. Even so, whatever you define, it will be the enemy of going to great. So I encourage you to get a higher SMART score. Now, what I want you to know is, if your SMART score is really low, if your SMART score is like, you drop back down to 30, you go down to like 36, and you notice that this number up here is like 25. Um, please ask for help. The last thing you want to do is frustrate yourself. You want to feel like a winner. So let's ask for some help and let's move forward. I hope you guys enjoyed the lesson. I know it was a bit brief. It was a 24-minute lesson. However, do you feel a little stronger about fractions? Why don't you give it a try? Make some mistakes and let's see what happens. I'm going to say 43 and make a mistake on purpose. And then I'm going to take a look to see what I did in my process that could have been a little bit better. I'm going to modify my process and say I got it. Don't just click through. Don't just go like, okay, well, I think it's this one. Oh, it's incorrect. Okay, and then click. Don't. If you do that, are we really learning? Or are we being individuals who like randomness? It doesn't seem to get us very far, but with genuine learning, you don't have to guess and you feel smart. My best wishes to you. Ask me if you need any help. Be more than happy to. Have a wonderful day.